Hi everyone, in this video we are going to review the ozone layer module. And so how I do my reviews are very simple. I basically just split them into two different sections. I have a context section, so that's the memorization, those are the facts that we talked about in this module. And I also have a chemistry section. Usually that's the more challenging part because it's a lot of application, and when on the exam we give you brand new problems that you have to actually apply this new knowledge to, so sometimes students find that to be the more difficult section. So as a way to remedy that, basically what I've done is I've added 3 problems, so at the very end we'll do the context, we'll do the chemistry, we'll hit the end, and we'll do these 3 problems to try to practice and solidify these concepts again. Alright, so let's start off at the very beginning, which would be number 1, which is our context section or our fact section, especially when we're talking about the ozone layer. Alright, so the first thing we talked about in this module is that ozone in the troposphere is bad. Okay, it's an air pollutant. But when we have ozone in the stratosphere, it is actually something that is really good. It acts as a protective layer for the Earth's inhabitants, which are primarily us, but it also protects plants and animals. And so this is something that's really good. So maybe we'll add protective layer here. Protective layer. So the very first thing that you need to do when you're studying for this exam is that you need to make sure that this is clear in your head. Ozone troposphere, in the area where humans are breathing it, it's bad, that's an air pollutant. Ozone in the stratosphere, where it's up higher, it's actually able to absorb that UV radiation and protect our skin, which is really nice. Alright, so then let's talk about it specifically here in the stratosphere. The ozone layer itself, okay, it's not the whole stratosphere, it's actually just the bottom half. And so for this course, we say that that is about 9.3 to about 18.6 miles above the Earth's surface. So that's what we consider the ozone layer to be. But in addition to this, we actually have learned that it's approximately 300 Dobson units thick, right? Dobson units thick, which is approximately 3 millimeters thick. So it's tiny. So what we need to know is that the ozone layer can exist anywhere between mile 9 and mile 18, but it's really only 3 millimeters thick. So it's not this huge cloud that's floating everywhere. It's just this teeny tiny thing, and we have to actually locate it. So we're really lucky that the small amount of ozone is actually able to protect us. All right, so then what we talked about was UVA, UVB, and UVC radiation, and how it interacts with ozone and oxygen. So for here, I'm just going to focus on ozone because I want to be specific. So when UVA hits ozone, essentially all that happens is the ozone molecule is able to absorb that radiation. When UVB hits ozone, what happens is it actually ejects an electron. And what's really bad is when UVC hits ozone, it actually forces the molecule to dissociate. And so this ozone molecule that has these beautiful 3 atoms actually breaks apart, and it's no longer able to act as that protective layer because UVC is such strong energy. All right, so then what we talked about was the relationship between ozone and UV radiation. So what we saw is that when we had a very high concentration of ozone in the atmosphere, in the stratosphere, we saw that we had a very low concentration of UV radiation on Earth's surface. I want to be very specific about this. So what we're doing is we're measuring the concentration of the ozone in the stratosphere, so up there 9 miles above, and then we're able to conclude something about the energy, specifically the UV energy on the Earth's surface. So we're talking about 2 different sections here. And then we can also obviously conclude the opposite of that. If we have a low ozone concentration in the stratosphere, what we see is a very high concentration of UV energy on the Earth's surface. So this is a bad situation. That's meaning that we have too much UV radiation is coming down and actually interacting with Earth's inhabitants. Again, humans, animals, dogs, whatever you want to call it. All right, we also learned how to measure ozone concentrations, and we have 3 main ways that we do this, but I'm just going to focus on 2 for this one. The first one is our Dobson ozone spectrophotometer. Okay, and that's just like a little tool that Dobson created to measure our ozone, specifically though to measure our UV concentration. And then we also have our weather balloons or our high-flying aircrafts. That's the second one, but I'm not going to focus on that. The last thing, or the most important one, is limb viewing. And so limb viewing is how we actually do this now and how we actually measure our ozone concentration. So this is the one that I find to be the most important, personally. We also talked about UV index. Remember, UV index was a way for scientists to communicate with non-scientists and actually tell them what the UV radiation is. And remember that we use colors. So I always expect you to know the ends in the middle. So green means good, not a lot of UV radiation. Orange is somewhere in the middle. There's some UV radiation. And then for this situation, we actually say that we have purple. So when you have something that has a UV index of purple, it actually has a value of greater than 11. And so it's a really, really bad. You never want to be outside if your UV index is purple. Never, ever, ever. All right, one of the last things we talked about in context of this section is that we said that there is an ozone hole, but it's primarily in the South Pole. And we spent a lot of time on this, actually, and we discussed how this happens and why this happens, which is probably more important. But the biggest thing, which we all know now, is that we create these things called polar, stratospheric clouds. Sometimes people just write PSC, but that's fine. But basically you need to understand how they form, why they form, and what is so bad about them. But basically the very, very bare minimum that you should understand is that they're in high chlorine concentration. So what happens is you have these clouds, they're just hanging out in the winter, not really doing much, and then they form these ice crystals. Now on these ice crystals, they're able to actually allow for this reaction to happen where they generate molecules that are photosensitive. Well, now you have all these molecules that are completely fine in the winter, but the second that sun starts showing up around September, these molecules start dissociating or decomposing. They're photosensitive, right? So they break apart in terms of light. You create these chlorine radicals, and the chlorine radicals then goes and attacks all the ozone. I'll show you that in just a second when we get to the chemistry side point. But basically what we need to understand, okay, is that there was this smoking gun graph. And what we were able to conclude is that when you have a very, very high concentration of chlorine, specifically a chlorine radical, you have a very, very low concentration of ozone. We were also able to conclude the opposite of that. So when you do not have chlorine radicals present, you have a very, very high concentration of ozone. So they're very, very easily able to conclude that these chlorine radicals are destroying our ozone layer. And so this is what we had to do, and we had to create something called, I say we, but I wasn't around for this, but we had to create the Montreal Protocol. Okay, so the Montreal Protocol essentially banned the global production of CFCs, or those man-made molecules that actually were really stable in the troposphere, but they go up to the stratosphere, decompose, and then destroy the ozone layer. So we have this Montreal Protocol, so I would be very comfortable with that piece of legislation. All right, so now number 2. Now we're moving on to the chemistry section. My favorite, which is probably not very surprising. All right, so now in this section, we didn't do too much of really complicated stuff, and especially when you get to the very end and you're studying for the final and you're looking back to this, I bet this section is going to be so much easier than it was the first time around. But for those of you studying for exam 2, this is basically what you need to focus on. The first thing you need to focus on is your atomic structure. So in our atomic structure, we basically know that we have some electrons, we've got some protons, we have neutrons, and this all happens in or around our nucleus. So now what I would expect you to do, especially the students that are here on campus, is be able to explain the experiments that were used to actually determine how we figured out where the electron is, where the proton is, and where the nucleus is. But you need to be very, very careful and understand the difference of this and absolutely understand what the charge has to do with these experiments, okay? The next thing we looked at were isotopes. And so what we did with our isotopes is we actually looked at things called atomic number and mass number. And basically what we were able to see is that isotopes have the same number of protons, but they have a different number of neutrons. So it's actually the neutrons, or the different number of neutrons, that make two things in isotopes. They have the same number of protons, a different number of neutrons. Hydrogen and deuterium is a very good example of an isotope. All right, so then we also talked about bonding. So we talked about ionic versus covalent bonding. So now we know an ionic bond or an ionic interaction is a full positive attracted to full negative. So it's an electrostatic interaction. Whereas a covalent bond is actually the sharing of electrons. So because covalent bonding is sharing of electrons, we are actually able to draw these type of molecules out, or these type of bonds out. And so we use something called Lewis symbols to draw or to visually represent these interactions. So the most important thing we know with Lewis symbols is that you always put the first two dots together. So hydrogen is one dot, helium has two dots right next to each other. If you moved on and then went to aluminum or something of the sort that would have three, you're going to go 1, 2, and then 3. So first two dots always go together. Then we have something like fluorine 1, 2, 3, 4, 5, 6, and 7. Okay? So make sure you're comfortable with the Lewis symbol. Symbol meaning one thing, one atom. And then we also have a more complicated version of that, which would be your Lewis structure. So a Lewis structure is used to represent an actual bond. So a Lewis structure is going to be something like this. So you have an HF bond, or maybe you want to do something very complicated and you have a double bond, another single bond, something like that. These are examples of Lewis structures. Structures are representative of a molecule specifically. Okay, now in this course, we always obey the Octet Rule. So what that means is that you can only have 8 electrons around each atom. So if we looked at this carbon atom right here, we see 1, 2, 3, 4, 5, 6, 7, 8. Beautiful. It has 8 electrons around it. Now, in order for me to count out the 8 electrons around anything else, the fluorines or the oxygens, I would need to draw in my lone pairs to make them accurate structures. So now with my lone pairs on the fluorine and now with my lone pairs on the oxygen, this structure is absolutely beautiful and it definitely obeys the Octet Rule. So that's good. The second thing you need to be able to do after drawing a Lewis structure, and this is kind of an important thing, is you absolutely need to be able to compare bond strength and bond length. And so what we can remember is for bond strength, what we know is that a triple bond is much stronger than a double bond, which is stronger than a single bond. But for bond length, it's the opposite of that. A single bond is much longer than a double bond, which is much longer than a triple bond. So you absolutely need to get these patterns straight in your brain and be able to draw them out, draw out your Lewis structure, then look at the bonds and say, okay, this one has stronger bonds or this molecule has weaker bonds, something like that. All right, so now we're moving away from Lewis structures and valence electrons, and now we're moving on to what's really fascinating and what's called electromagnetic radiation. Okay, and sometimes I abbreviate this as EM radiation. It just depends on the mood and how fast I'm trying to write, but that's what we're talking about. So the first thing you need to know is you absolutely have to get down your electromagnetic spectrum. Okay, so by now I'm sure you have this down, but just in case it's not there, we know that gamma rays are higher in energy than X-rays, which are higher in energy than UV, then Vis, then IR, then micro, and I'm running out of room, so we'll put radio here at the end, but we absolutely need to have that spectrum in that order. You need to know high energy, gamma rays. If something is high energy, then you also have a high frequency, which means you're going to have a really small wavelength, okay? So make sure you have all of those properties together. Now, we know that our electromagnetic radiation is just a very good way to describe an electric field and a magnetic field that are propagating through space together. But the biggest thing for these is that we have to remember that they are perpendicular, okay? An electric field and a magnetic field, they're perpendicular, but together they propagate through space, okay? Now, the big question, how fast is everything moving? Well, everything always moves at the speed of light, which is a constant c, and it's 3.0 times 10 to the 8th meters per second. You must have that unit down, okay? That's super important. Okay, now, once we're there, we use a lot of different formulas to actually figure out how to go from wavelength to frequency to energy. And here are our 3 main ones. So the first one that we talked about is that our speed of light is equal to our wavelength times our frequency, okay? So speed of light's our constant, wavelength is going to be your inverse, or excuse me, it's going to be your meter component, and then your frequency is going to be your inverse time component, okay? So that's your one. The second one would be E is equal to H times nu, where H is Planck's constant, and so Planck's constant never changes, so we have H is equal to 6.626 times 10 to the negative 34th, and that unit is joules times second. Now, we can combine these two equations here and come up with E is equal to H times C all over lambda. So basically what I would do is memorize all 3 of these and make sure you can use all 3 of these very, very easily, and basically not stutter or have any issues with them when you get to a problem. But please remember, I will always, always, always give you constants, but formulas you have to know. You have to know all the formulas. All right, now, electromagnetic radiation travels in photons. but we all know that photons are essentially just bundles of light. And now this next section is primarily for my on-campus students, but just, you know, it's fine. Everybody can listen. And so essentially what we have are quantized energy levels. And so when we have quantized energy levels, what that means is there's very, very discrete energy levels that an electron can travel to. It's like stairs. It's not just a big spectrum here. It's very, very distinct that at which an electron could actually sit in these specific energy levels. And so what we talked about, and this is the part I'm talking about for on campus, is the photoelectric effect, which basically just says there's a minimum amount of energy required in order to eject an electron, or a lot of times we refer to it as a threshold frequency. And we use the photoelectric effect to prove that light behaves in a particle-like matter. Okay. And then we also had X-ray diffraction. And so X-ray diffraction was another type of experiment, but basically what we saw is that light can actually operate as waves as well. So what's neat is when you take both of these two sections together, what you end up with is something called wave-particle duality. So your photons can act like a particle, but they also can act like a wave. And so together, we say that they act like in both pieces. They act like a particle, act like a wave. All right, so then moving away from electromagnetic spectrum or radiation in general, what we did is we talked about the Chapmans cycle. So the Chapmans cycle is something you just have to memorize. You need to get this down. It's one of our first mechanisms that we look at in this course. And so basically what it is, and I'm just doing the simple version, you need to know way more than this, but essentially what we're saying is we have oxygen can move to ozone and ozone can move back to oxygen. And we're in this continuous cycle. So in theory, we're never going to run out of ozone and we're never going to run out of oxygen. That being said, unless we actually get to a point where all of our CFCs are breaking everything apart. Now, like I said, unless you have two different things. So we have water, which breaks apart into a hydrogen radical. We have N2O, which can break apart into an NO radical. These two sources are natural radical sources. Or we have CFCs, which break apart into chlorine radicals. Now, any three of those, when you treat those with ozone, they decompose to create oxygen. So all three of those things actually destroy our ozone layer. The last thing we talked about were CFCs. We know that they're man-made, they're non-toxic, they're non-flammable, they're absolutely perfect for everything that we need them for here on Earth, especially when they're interacting with humans, except for the fact that they destroy our ozone layer. Okay. And so the best thing we need to know is that we have created some replacements for CFCs. And so our CFCs are chlorofluorocarbons. We've created hydrochlorofluorocarbons. We've also created hydrofluorocarbons. But our best option right now are hydrofluoroolefins, so HFOs. Those are absolutely the best. Okay, so those are the ones we want to focus on. Whoops, that just jumped up. So HFOs are the best. All right, so what I'm going to do now is give you just a minute to work through a couple problems. So go ahead and start with this first one. My computer's glitching. There we go. Go ahead and start with this first one here and draw out that Lewis structure. Go. All right, did you do it? Were you able to draw out the Lewis structure? Hopefully you were, but just in case you weren't, don't worry. Usually when you're drawing something out with this structure, when it's complicated, start on the left side and move to the right. So you start with your carbon. Everything that's written after the carbon is attached to that carbon. So these hydrogens are attached to that carbon. These hydrogens are attached to this carbon. And so what you can do is kind of very, very slowly go through and build your structure. So what I see here is, like I said, start with your carbon. Here's my carbon. It's attached to 3 hydrogens. So 1, 2, 3. All right, so then we have another carbon. So my carbon's attached to a carbon. This carbon is attached to 2 hydrogens. So 1, 2. All right, now we're attached to another carbon down here. That carbon is also attached to 2 hydrogens. So 1, 2. Now this carbon is attached to an alcohol, so an OH group. So the carbon goes to the oxygen, which is then attached to the hydrogen. We have 2 lone pairs on your oxygen. So that is your complete Lewis structure for what is called propanol or isopropanol, okay? And so this is something that is a structure that has 3 carbons in it, several different hydrogens, and an alcohol group. So hopefully you were able to do this. If not, stop really quickly and ask some questions, okay? All right, now, moving on. What's the next question? What is the wavelength of a photon of light with 4.96 times 10 to the negative 19 joules of energy? Go. All right, did you get an answer? Hopefully you did. If you didn't, that's okay. We'll work through it together. So the first thing you have to do is identify some information. So I see that it's giving us an energy of 4.96 times 10 to the negative 19 joules of energy. Now it's asking for a wavelength. So the only equation we have in this module that equates wavelength and energy is right here. So we know that H is a constant. That's Planck's constant, 6.626 times 10 to the negative 34th. That's joules seconds. And then we have C, which is our speed of light. So 3 times 10 to the 8, which is meters per second. Oops, that should be a second. And so now both of these constants will absolutely be given to you on an exam, but formulas will not. So you need to make sure you know that. So now we have all of our information. All we have to do is plug it in. So we have our energy, which we just said was 4.96 times 10 to the negative 19 joules. We set that equal to Planck's constant, so 6.626 times 10 to the negative 34th, that's a joule second. And we multiply that times our speed of light, so 3.0 times 10 to the 8th, which is in meters per second. Now we divide all of this by wavelength. So if you do this properly, you're going to get a wavelength that is in meters. So you should get an answer that is something like 4.00 times 10 to the negative 7th meters, which we then could convert to something that means something to us, which would be about 400 nanometers, okay? So please remember, you absolutely need to know the range of your visible spectrum. So 400 is going to be your blue light, and then your 700 is going to be your red light. So blue light is going to be in much higher energy, so we need to know that, okay? All right, so hopefully you got that. If you didn't, remember, ask a teacher or shoot me an email. All right, last one, go. All right, did you get an answer? Hopefully you did. If you didn't, do not worry about it at all. You just need to do a little bit more practice. So let me just draw these out for you here. So hopefully this is what you got. The first one is propane. Okay, so this is propane, C3H8, and then we also have propene, which would be C3H6. So C3H6 or propene has a very unique structure. There's 3 hydrogens on the first carbon, 1 on the second, 2 on the third, and then you have this very important double bond between these carbons. And so immediately when you see where we're looking for stronger bonds, you identify either a double or a triple bond. You know those are significantly stronger than a single bond. So propene has to be the correct answer. Hopefully that makes sense. If not, please email me or ask your teacher. If not, good luck on your exam. Good luck on your final. Please take care of yourself, study hard, and drink water.